Okay, let's get started. So it's my great pleasure to introduce Akshay Narayan. So Akshay is a PhD student at MIT working with Mohammad and Hari, and he's going to be talking about Bertha, which is some work that we've been doing on how to evolve network APIs to better expose programmable networking elements to the application. Akshay, you should take it away. Akshay requested questions during his talk. So let's, as a protocol, if you have a question, why don't you just, if you can hit the raise hand button on your participant thing, I can interject and have you unmute and talk. Thanks. Sorry, Akshay.
Yeah, and since I don't know most of you, it'd be great if you could just quickly introduce yourself if you have a question. Yeah, okay, so let's get started. So I guess I'd like to start with a discussion of history and this sort of simplified picture of the internet architecture. And architecturally, the assumptions made by internet APIs are exactly what this picture shows. So best effort end-to-end packet delivery. And we've had this picture since the beginning of the internet, described in Dave Clark's paper, which we all read as, at least it was for me, it was my first paper, first networking paper that I read. And this API has sort of led us through a tremendous period of growth in the internet to the point where a pandemic can happen and everyone can do all their talks virtually and things hopefully mostly work out. So that was the architectural picture of the internet. And now let's look under the covers into the infrastructure of the internet that supports that architectural API. And we have our routers, which were originally all that we needed to support this architectural API. But moving a bit forward in history, our network operators added new functionality into the network for various reasons. And the slide says safety, efficiency, and telemetry. But beyond that, there's all kinds of stuff that network operators put boxes into the network to do that aren't strictly necessary to fulfill this best effort end-to-end packet delivery semantics and API. So, of course, people eventually wanted more flexible functionality, and they put fancy new devices into the network more recently to help with this, to perform these network functions. So, for example, people have used these devices in middle boxes to do custom telemetry queries with fancy sketch algorithms, and this is still an active area of research. So there was a paper just last week at OCI about using an FPGA to implement a really efficient firewall. And another example is the Azure VFP system, which we heard about at NSTI a couple of years ago, where programmable hardware offloads handle virtual switch functionality in production in Microsoft's data centers. So while these devices were originally intended to support our network operators' goals, researchers, we tend not to leave opportunities lying around. And once the network becomes programmable, the cat is sort of out of the bag. We can use those devices for basically anything, and we might as well do so. And correspondingly, in the past several years, we've seen proposals and deployments by researchers of a new set of functionality for computer networks, which is the acceleration and optimization of application-specific functionality. And I put a couple of examples on the slide, the hardware acceleration of key value stores, load balancers, and consensus protocols. But again, this is another increasingly popular, especially recently, area of research. And it turns out that having functionality in the middle of the network enables performance optimizations that aren't possible with our traditional end-to-end application semantics. So because these performance optimizations aren't otherwise possible, we can probably guess that both the programmable hardware in the network and the use of that programmable hardware, or at least the desire to use that programmable hardware for application optimizations, is probably here to stay. So that's the sort of background of the talk. I'll now go into a little bit of a motivation section with how things work with this setup today, along with some complaints about how certain aspects of this are suboptimal. Then I'll go into our proposed answer to this question and some of its interesting implications. There's also a good time to warn you that there's no eval ahead. This is a work in progress. And of course, any feedback that you have would be greatly appreciated. So let's start by seeing how the use of hardware offloads for an application's development and deployment plays out in an example application. So our server in this example application, which let's say is a key value store, has two shard processes, and each shard is responsible for half of the alphabet in terms of incoming requests. So When we go about trying to develop this application, one of the first things that we have to decide, now that we've decided that we want to potentially use these new hardware offloads, is how we're going to implement our sharding based on what is available in the network that our application is going to run on. This means that we have to figure out what devices and hardware targets are available in the network, or maybe buy a new device and convince our network operator to deploy it. We then have to write an offload implementation of the appropriate slice of application functionality that works with our idea of what the rest of the application will be doing. We finally then have to write the rest of our application in a way that assumes the presence of the offload that we just wrote. So for example, to make this a little bit more concrete, in our sharding example, we might implement optimizations that, for example, take advantage somehow of key similarity because it's only each shard is only handling a subset of the requests. But these optimizations then assume that the sharding is being done correctly. And of course, these steps have interdependencies which complicate things. So certain hardware targets are more suited to certain types of offloads, and that also affects what our development path of our overall application is going to end up looking like. So now we've sort of written a bunch of code across both the application CPU and hardware offload targets, and we have to actually get our code to run in both the server and the network on which the server is located. So first, based on the offload implementation that we wrote, we have to run the offload on the right piece of hardware. And then we have to make sure that this offload actually processes our application's packets. So we have to configure routes in our SDN control plane to make sure that this happens. Then on the server, we have to configure the operating system and actually run the software component of the application. So also consider that there are multiple slices of application functionality which we might want to offload. So in our one single application, which is the key value store, we can have a transport functionality, which is aided by a segmentation offload, and then also a sharding layer on the SmartNIC, which puts requests onto the right CPU core for that shard, and then a caching layer out in the middle of the network somewhere on a P4 switch. So one interesting implication to note here is that we formed an implicit processing pipeline of offloads, which sort of snakes through our network, since the path of messages from clients towards the server at the bottom of the slide, there can be different pieces of application functionality applied in different places of the network. So for example, some functionality like sharding, there are actually multiple paths that we have to consider because the application functionality is actually rerouting the messages to different shards. So we actually really have, if you think about it, a DAG of functionality that's implicitly included in the deployment of these offloads into our network. This means that we have to carefully think about where to deploy each piece because our choices can affect both performance and semantics. So for example, if we deployed sharding on the P4 switch instead of the other way around and caching on the SmartNIC, the sharding could route not just to a core on our server, but to a different server entirely because it's in a switch rather than on a SmartNIC. But on the flip side, the caching will have to deal with an entirely different access pattern because it's seeing the request for only a single shard. So whether or not we want to flip these or we should flip these depends on the exact application we're running and what we expect our workload to be. And it's not entirely clear, and sort of smart people have to think and sit down and think and figure out where to implement each piece of the DAG of this functionality. So now let's move on to a little bit more of the complainy side. And the main theme is going to be the implicitness of the applications network API. So this isn't just the traditional sockets API, but also more recent and popular APIs like DPDK and libraries higher up the stack like gRPC and Quick, which tend to embody this architectural sort of tunnel vision because the architectural semantics of the network tell us that our application is inside a tunnel with only these best effort semantics. And I'm claiming that this architectural API is the reason for all the implicit state that we've seen over the last couple slides. So the main cost of the implicit state is out-of-band coordination. This is unfortunate because it makes adopting in-network offloads difficult. So to deploy such an offload, we need to sit in meetings and send emails until various people agree on our deployment strategy. Then because of the meetings and emails, it becomes harder to change applications, so we get ossification. So if we started out, for example, with a Redis offload, we can't switch, or it's very hard to switch to memcached later because all our offloads would break and we'd have to go through this implicit coordination step all over again. Another thing that we've lost with implicit state from having a common set of semantics that application network libraries depend on, and this applies both to the newer, fancier APIs and as well as the classic sockets API, is portability. So if my application uses just sockets, I can decide one day to move from hosting my application in Amazon to hosting on Azure. And all I have to do is update my IP address and DNS settings, and things sort of work out. But if I've configured fancy offload features that Amazon has offered for me, for example, like elastic load balancing, ELB, this becomes way harder. And one way to think about what's happening here is to think about like S3 compatible APIs. So like if my application accesses some like storage service, and that storage service happens to be Amazon S3, then my application source code has a bunch of S3 API calls in it. And if I want to switch to a different storage provider, then if that storage provider doesn't offer S3 compatible APIs, then I can't just switch the IP address of the storage endpoint and then have everything work. I have to change my use of the APIs. So what's ended up happening is that a lot of storage services will tend to offer S3 compatible APIs to offer this portability. But this same kind of S3 compatibleness doesn't exist with the idea of using hardware offloads for my application. So our answer to resolve this question is a new application network abstraction, which we call channels, and a new interface to that abstraction, which we call Bertha. And the high level idea, the proposal for addressing this issue is to enhance the application's network interface to perform offload related coordination. And what we want this interface to do is provide a way to talk about an application's network oriented functionality. So from the application developer's perspective, they declare upfront all the network functionality that they could benefit from. And then, and then the offload developer is responsible for providing one or more implementations of that functionality. So the idea of a channel comes from the idea of network tunneling, which is widely used today to enhance our vanilla end-to-end delivery with additional network-specific information, such as labeling. A channel is a fancier version of a tunnel with more rich semantics. And applications use channels by interfacing with the Bertha library, which is named after a tunnel boring machine in Seattle. Each tunnel type represents a specific piece of application relevant functionality that can be offloaded into the network. The channel type encodes some semantics which the application wants the network to provide. For example, the sharding that we were discussing earlier. So a key insight here is that just like the application can use the libraries above the level of sockets to change the semantics that the application code experiences. For example, we can use gRPC and TCP to give us RPC semantics instead of best effort packet semantics. We can similarly layer libraries above packet delivery that are offload aware. So if we know the semantics that the application wants, then architecturally, as far as the application is concerned, it really shouldn't matter where the offloaded functionality is implemented. It could be in a P4 switch in hardware, it could be an eBPF in the kernel, or it could be inside the application itself. So as long as the semantics that the channel that the application specified are followed. So in this sense, a channel is just something that changes the semantics that the application wants the network to have. So therefore, channels sort of provide a unified abstraction for all communication-oriented application offloads, no matter how they're implemented. And our deployment story from earlier, where deploying an offload involved out-of-band coordination, has now become much simpler. The developer specifies that the application can benefit from some offload semantics, and the Bertha library makes sure that that functionality is available from the application's perspective when it uses the network. It's important to note that this isn't magic. So all of the same work that was happening before is still happening. But the main change that has happened is that the work is in band instead of out of band. So what do I mean by this? So the offload here is responsible for configuring itself to work. And this includes all of the things that we talked about before. It's like the controlling the SDN policy and any potential control plane actions like a data plane reconfiguration. The application has to say which slices of its functionality can benefit from the semantics of a given channel and how the composition between these slices of functionality or channels works. So while no less work is happening, no extra work is happening either. All the same things are happening, except the the interface and the communication is in-band instead of out-of-band. So when implementing our channel interface, we have three goals to keep in mind: portability, safety, and compositionality. So we've come up with some rules that channels should follow so that providing these goals is possible. Let's first look at portability. Let's say that we have this scenario where our application is running in a network in which there are no fancy hardware offloads available. So in this case, the functionality still needs to be implemented somewhere. And the only place that we have available to us that's left is in software in the application. And we call this property fallback. So while a fallback implementation will probably have worse performance than an hardware offloaded one because it's running in software rather than hardware, it ensures that we can have portability and the application can still function in the absence of any fancy hardware offloads. So next, the application developer gets to decide which channels the application wants to use. However, to ensure safety, network operators are still entirely reasonably want to restrict how traffic is forwarded, for example, by using a firewall or a billing middle box. So applications shouldn't be allowed to bypass this functionality because while we'd all like to use the internet for free, billing middle boxes are probably something that we shouldn't be bypassing. So channels, as a result, have to be application relevant. And this property of application relevance is what distinguishes channels from work in NFs. So while the goal of an NF is, as we saw in the very beginning of the talk, to provide some functionality that the network operator wants to operate the network safely, correctly, and efficiently, the channel's goal, on the other hand, is to aid applications instead. Finally, compositionality is important because applications may want to use multiple channels together. So in this example, the application is specified that it wants a channel with encryption, with HTTP2 semantics, and a reliable TCP connection. The application specifies a set of channels. So the semantics of each channel are layered together into a connection, which is Bertha's fundamental unit of abstraction, kind of like a socket in the traditional sockets API. So channel instantiations are per connection. So for each connection that the application is using, Bertha will instantiate an offload configuration that meets that application's requirements for that connection. Okay, so how does Bertha actually work? So it has two primary jobs: discovery, which keeps track of the set of channel implementations available in the network, and negotiation, which decides which implementation of the ones available to use. So let's remember this figure from a few slides ago. The offload needs to tell the application somehow that it actually exists and it is usable. After that, from the offload's perspective, Bertha can tell it the configuration to use corresponding to a given connection, and then the offload can set itself up using whatever external and internal scripting to make sure that everything works out for that connection. So this is exactly what the discovery process is for. And you can imagine this process working kind of like DNS. It doesn't literally have to be DNS, but it serves a similar purpose. So the fallback implementation will always register itself with the discovery service so that we can always be sure that the application will run. And if Bertha finds out that there's no offloaded implementation, then it'll use that fallback implementation. But in the case that there are multiple implementations available, that's where negotiation comes in to pick between them. So how does negotiation work? So in negotiation, Bertha gets this set of channels from the application, and it goes through the negotiation process for each of those channels. Negotiation also ensures that for the channels requiring it, the functionality might need to be present on both ends of a connection. So in this case, both encryption and decryption are required on the two ends of the encryption channel for things to actually work out. And you can sort of think of negotiation as analogous to like listen and connect in the sockets API. So there are a number of considerations that we would want to take into account during negotiation. And if I try to run my application on a vanilla network without any available offloads, negotiation is what makes sure that the fallback implementation is used instead. As another consideration, the network administrator might want to specify a priority order for the application's use of offloads. For example, we can imagine a cloud provider using the system to offer the use of a P4 switch or some other piece of hardware to higher paying customers first, and then also allow lower paying customers to benefit from that hardware if there's spare capacity available. So I'll go into this last section of the talk by exploring some open questions that we're excited to find answers to going forward, as well as making some observations about how the application's view of the network in Bertha has changed from the traditional view that we have today. First, as we saw with negotiation, how should Bertha decide which tunnel implementations to use for a given connection? So this is sort of similar to the role of a cluster scheduler, except we're scheduling connection offloads instead. So let's, as another example, let's consider this example where the application has specified a TCP tunnel inside an HTTP2 tunnel inside an encryption tunnel. And we have a SmartNIC available, which offers implementations for both encryption and TCP. To use these offloads as is, we'd have to traverse the PCIe boundary to the NIC 3 times. So first for the encryption channel, then back to the CPU for the software HTTP2 implementation, and then back again for the offloaded TCP implementation. If we rearrange this channel specification, then we can save significantly on the data movement costs. And of course, this idea is not new. This same kind of optimization is similar to those performed by TensorFlow and ONNX in the machine learning domain and Weld in the data processing domain. The idea is that because the channel semantics are explicit rather than out of band, we can apply optimizations to them. And of course, a challenge here will be to ensure that the right semantics are preserved. For example, in this case, we moved the encryption channel, which means that the HTTP2 headers were not encrypted before, but are now encrypted. This might be bad if there is some interdependence between that HTTP2 channel down the stack and another channel which was depending on reading those HTTP2 headers. We also saw this earlier in the talk with the sharding and caching example. The advantage here of this having Bertha is that we can write things down in a format that we can reason about and have more hope of resolving these semantics issues outside of manual out-of-band interactions. Another cool implication is that it's entirely semantically valid for the channel implementation to reside not on special hardware, but on a cooperating client. For example, if the server wanted to shard incoming requests, it could push this functionality all the way to the client and remove the need for a fancy offload altogether. And the client would send data directly to the correct shard. In the paper, we show that this configuration can improve scalability and performance, and I promise that's all the eval talking that you'll get from me today. Normally, this would be difficult because the developer would not want a hard code sharding policy in a client, which is hard to update. But in this case, because the sharding policy is per connection, offloading to the client doesn't actually lose us anything. If we wanted to change the sharding policy, we would just update our application, and the sharding policy would propagate through Bertha through the discovery and negotiation processes to the client, which would then use that new policy for subsequent connections. So let's finish with this thought. Networks have become more programmable in the last few years, and our community, including some of the people here, have shown us that applications can really benefit from this. And the question that's been left unanswered so far is, how should an application developer go about actually using all this great new research? Without an answer here, only a few people will be able to benefit from these ideas because it'll be too hard. Like, you'll have to do too much extra coordination, just like how the storage servers are forced to adopt S3 compatibility for their APIs. Not everyone is going to be able to do that. So Bertha is our potential answer to a way that applications can evolve to incorporate this new functionality. There are, of course, probably other answers that are valid, but definitely we think that answering this question should be a part of the conversation. And I'm happy to take your questions about this or about anything I talked about other than that. And so that's all I have. I'm happy to open it up for discussion.
Thanks, Akshay. Yeah, so if there are questions or comments, now's a good time to give them. I am involved in the work, so it's a bit weird for me to ask a question. So I guess to get the conversation going, or as a question, right? So one of the things that's that work like Bertha, or in general, this literature is doing, is pushing application semantics into the network. So like, does it really make sense for a large number of applications to have access to these semantics? Like, isn't there an issue that we're making our networks more complicated, and we already have spent, like, I don't know, the last 10 years of literature talking about how networks are super hard to get right. So aren't we just increasing the burden on the operator?
Yeah, Panda, I think that's a good question. I think no matter what you or I say, I think the network is becoming complicated without us, and people are going to sort of do this stuff, offload parts of their applications to things in the network anyway. So if we can do what we can to make this more elegant as a deployment method, then I think we should do that. And
they can get Jan's schedule.
Sorry?
I think it was just an accidental thing. I'm not sure.
Okay, yeah. But I guess that's my answer. There's no point fighting complexity, so we might as well embrace it, I guess. Or hide it behind a layer of abstraction.
And I guess if we don't have sorry, are there other questions?
No, I was just gonna say, if people are sort of tired of me, then we can always end early and go have chai. So
yeah, I mean, so that was what I was about to suggest. So like, if there are no more questions, we can just end early today. So. Okay, let's give it a couple of minutes and then